Hi there. In this video, we're going to talk about the Laplace transform of periodic functions. So we begin by first understanding what exactly is a periodic function and what we mean by that. So very simply, a periodic function is just a function that repeats itself. You can see in the curve in red, we have some kind of arbitrary function, and you can see that after some time later, the function starts to repeat itself. And that time we designate by the capital letter T, and that's actually called the period. So the period is the amount of time that it takes for this function to start repeating itself. You can see that after t, the function goes through another cycle, and then 2t later, it goes through another cycle, and then 3t later, it would continue in that manner. So we would now want to take the Laplace transform of this repeating function like this. So we would firstly need to gain some kind of mathematical description of it before we can even try to take the Laplace transform of it. So what we can do is that we can give a name to each one of these parts of the curve. So we'll call this one f1 as a function of t. Then the second segment, we'll call it f2 as a function of t, and f3 as a function of t, and it would continue on in this manner. So if we wanted to just write f1, so we would say that f1 as a function of t is, firstly, it would take on different values, right? So it would take on the function of ft, it would take on f of t in the range between 0 and t, so where t is between 0 and t, and it would take on the value of 0 everywhere else. So we'll say 0 otherwise. And if we look at now at the second cycle is exactly the same as the first cycle, except that it's just shifted by a few units. So what we need to do now is we need to somehow state this function in a way such that it's written in terms of f1t, but we somehow cancel out the function everywhere else. And is there a way of doing that? Yes, there is. You'll see that in the last video, we spoke about the Heaviside unit step function. So if you are unfamiliar with what this type of function is, then you should probably just go back and have a look at that video before proceeding. So what the Heaviside unit step function does is that it allows us to basically switch on the function at different points in time and switch it off or even activate it. So that's what we're going to do. We want to say that we want to activate a function within different periods. We want to switch on the function from this period, from this time to that time, and then switch it on again from this other time to this other time, like that. So we have written f1 as a function of time, and we're just saying it's just the function between 0 and t. So with f2t, what we're going to say is that it's the same as f1 of t, okay? It's the same as f1 of t, except that maybe if we're here, let's just say t is here. If t is there, and we want it to be there because we're saying it's f1t, then all we do is that we displace t by the period, okay? So if we take this value of t and we then minus it by the period, then we're actually just reading off the same value. So we can say that it's t minus the period capital letter T. And what we can now do to switch it on during this period of time, we use the Heaviside unit step function. And you would recall in the last video, it's written as u, and we would say t minus t, capital letter T. So what this says is that it's switching on f1 t minus t, basically with t being between t and 2t. So that's how it actually works. So if we wanted to write f3, we would do it in the exact same way. We would say f3 as a function of time is equal to f1, but in this case here we'll have 2t, okay? We'll need to subtract 2t. There's 1t and there's 2t. So we'll have t minus 2t into u minus into t minus 2t. So we have written each of the sections of the graph in this manner, and we can simply just combine it. So how we would combine it is that we would write it as a function of t, which is what we want. We now have a generalized function of t, and it's equal to, well, this first portion f1 of t, and then we have plus, and this second portion is f2, so there's f2 of t here, and what it's equal to is f1 t minus t times this Heaviside unit step function, and that's u into t minus t. And then we would have f3, and f3 we know is f1 into t minus 2t multiplied by Heaviside unit step function into t minus 2t. So this u t minus t switches on the function during this period of time here between t and 2t, and this u of t minus 2t switches on the function between 2t and 3t. However, if we look at f1t, we do need to say that the function is only during this time from 0 to t. And how would we do that? We would need to apply the Heaviside unit step function between 0 and t. So we would say u in t, because t we would say is equal to 0. So that's how we say now that it's only switched on between 0 and t. So this is our generalized function of t. We now have a mathematical description of this periodic function, and we now need to take the Laplace transform of this function, which we can see is the sum of these different parts of the graph, and we need to carry on in this manner. So how do we go about doing this? Well, all we would do is we would take the Laplace transform of each term. So the Laplace transform of this function of t, so that's equal to this Laplace transform of f1 t times u of t plus the Laplace transform of f1 t minus t times u of t minus t plus this Laplace transform of f1 t minus 2t times u of t minus 2t, and it would carry on to infinity. So now we're faced with another problem. How do we address now taking the Laplace transform of this Heaviside unit step function? How do we incorporate that as part of the Laplace transform? Okay, so we just need to just understand that quickly. So we can do it for each term, but let's just isolate this second term. Let's take the Laplace transform of it and get an understanding of how we account for this Heaviside unit step function. So what we're looking at is the Laplace transform of this term, and that is f1 t minus t times Heaviside unit step function u of t minus t. So as is always the case, we commence with the definition. We apply the definition. And the definition of the Laplace transform is that it's the integral from 0 to infinity, this function here, which is f1 t minus t, and Heaviside unit step function which is u t minus t, and multiplied by e to the minus st. That is how the Laplace transform is defined, dt. So how do we address this? Okay, so what we're going to do is we're going to now take out that term, okay, the Heaviside unit step function of t minus t times e to the minus st. So now this is going to equal to, it's going to take on two values. It's going to take on the value of, firstly, 0 between t and 2t. Okay. So remember now that we have taken this second term. And you can see that the second term is valid for this part of this graph between t and 2t. So that's why we've written it like that. Sorry, my apologies. That should actually be from 0 to t. And then it takes on the value of e to the minus st between t and 2t. So what we're saying is that we have to apply this integral between this range here for it to be actually valid. So that's what we're going to do. We're going to say now that this Laplace transform of this function f1 t minus t u of t minus t is equal to this integral between t and 2t, and we're going to have f1 t minus t, we just write it as it is, and now this term, this combined term of u into t minus t times e to the minus st, we're saying that this takes on the value of e to the minus st in this particular range. So that's what we're going to write, dt. So this looks a bit different now from our traditional Laplace transform, and we sort of need some kind of manipulation here to get it into our standard form for us to get some meaningful results out of this whole thing. So let's try to understand that. Let's try to do some manipulation here. So what we're going to do is some kind of substitution. So we will substitute v. We'll say v is equal to t minus t. So what that means is that t is equal to this capital letter T plus v, and also would imply that dv is equal to dt. So we can write this integral in this manner. And when we do that, what we get is this Laplace transform, okay, this integral, and we can see now that v is equal to t minus t. So if we have t here, we have t minus t, which is equal to 0. And then we have 2t minus t, which is t. Then we have f1, and this t minus t is v. And we have e to the minus s into t, and t is this capital T plus v. So we write that in, dt. So this minus st, we can bring that out because that is a constant, right? Remember that this period is a constant. And this s is also a constant. So e to the minus st is a constant. So we bring that out. We have e to the minus st. That's capital T. And then what we're left with is the integral from 0 to t of f1. And we can just substitute it back in. So we have v is t minus t. And we have e to the minus st plus, we just left with this v. So minus sv. And this v, we know that it's just t minus t. We can write that, so that's t minus t dt. So this is actually a very interesting result, and we just need to understand one thing. We have to understand that this f1 t minus t is just the same as f of t. So let's write that. So this is equal to e to the minus st times the integral from 0 to t of f1 t minus t. So this f1 t minus t, if we go back up to our diagram, this here is f1 t minus t. However, we can see it is literally the same function, right? There is no actual difference in terms of the function between these two different parts of the graph. It's just the case that it's in a different place. So this function is actually the same. So the Laplace transform of the function in the first segment is going to equal to the Laplace transform of the second segment. So this f1 t minus t can just become f of t. We can just write this here. So that is f of t, and we have e to the minus st dt. And this is our standard form of our integral of the Laplace transform. The only difference here is that instead of going to infinity, we have to this period t. And we'll just write that in a certain way. We'll just give it a name. So we have e to the minus st, and then now we're going to multiply it by this Laplace transform as we normally would do, except that it's being taken to this period t instead of infinity, and we'll write that as f1s. So that's what it is. That's what it is. So this e to the minus st f1s is what corresponds to the second term of this function that we had taken. So let's just go back up and remind ourselves what we have done and what we're considering. We are considering this second term of this Laplace transform. So let's just write out that expression again, and we can do a substitution in there. So this equation that we were considering was that f of t is equal to, and let's just remember that we are considering the Laplace transform of it. So we're considering the Laplace transform of f of t, and this was equal to the Laplace transform of f1 t times u of t plus the Laplace transform of f1 t minus t times u of t minus t, and you can write one more term, Laplace transform of f1 into t minus 2t times u of t minus 2t. So what we have seen is that this term that we've just written, this is equal to this term that we have just derived. So that's equal to e to the minus st, okay, sorry, that's capital T, times f1s. So if we were to do this same procedure for the other terms, we would get the exact same thing. However, instead of minus st, we would have minus 2st. So this third term is going to be plus e to the minus 2st times f1s. Okay, here we had t and we have minus st. So if we do the same substitution, instead of t, we'll have 2t. So that's how this minus 2st comes there, and it would carry on in this manner. And we would also have the same thing with the first term, except that the first term will just be f1s, because there's no t minus t. Basically, t, capital letter T is equal to 0 in this first term. So what we can do is we can take out f1s as the common factor. Let's do that. So we have f1 s into 1 plus e to the minus st plus e to the minus 2st plus e to the minus 3st, and so on. So this term within brackets, we can actually see that it converges. We can use the binomial theorem. So let's just remind ourselves quickly. So if we have 1 plus x squared plus x cubed and so on, this is equal to 1 over 1 minus x. That's by the binomial theorem. So similarly, we just substitute x with e to the minus st. So we have 1 plus e to the minus st plus e to the minus 2st plus e to the minus 3st, and so on. And this is just going to give us 1 over 1 minus e to the minus st. So that's what this entire term in brackets comes to. So what we have literally just shown, if we bring everything down here, is that the Laplace transform of our periodic function, f of t, is equal to f1s multiplied by that, which is 1 over 1 minus e to the minus st. So that is it. This is our main result. That is our main finding. This is the Laplace transform of a periodic function. And this is the derivation associated with that. So how would you implement this? you would implement this exactly as the way it's written. So if we have some kind of periodic function, we'll just do a simple periodic function where we have just something repeating. Maybe that's repeating like that. Then it's coming down, and then it's going again. Maybe this is our repeating function. Maybe that's 3, and that's 2, and that's 4. We can see that our period is 4. So t is equal to 4. So our function, f of t, is just equal to 3. So it's just taking on the value 3. And our period, t, is equal to 4. So how would we find the Laplace transform of this repeating function? So what we would do is we would apply this formula. We would say the Laplace transform of f of t is equal to f1s times 1 over 1 minus e to the minus st. So we have 1 minus e to the minus st. I'll write that first. And remember that this t is equal to 4. Right, so we can write that in. So it's minus 4 times s. And this f1s, let's just remind ourselves what that is. Just go a bit up. So this f1s, we can see in this derivation, was the integral from 0 to t of f of t e to the minus st. So let me just write that down here. So f1s is equal to the integral from 0 to t of f of t and then e to the minus st dt. Okay, so we have the integral from 0 to 4. However, we can see that from 2 to 4, this value is 0. There's no value there. So this integral is going to be 0. So there's no point in integrating from 2 to 4. So we can just integrate from 0 to 2. Integrate from 0 to 2. And f of t, so that function is just 3. So we have 3 times e to the minus st dt. Then we have 1 over 1 minus e to the minus 4s. That's 4s. And we just integrate that. We can bring out this 3. And if we integrate it, integral of e to the minus st is e to the minus st. And then we have to divide by minus s. And this is integrated from 0 to 2. So this is now equal to 3 over 1 minus e to the minus 4s. That's 1 minus e to the minus 4s. And then once we substitute in, we'll have e to the minus 2st, and then e to the power 0. E to the power 0 is just 1. So we have 1 over s here. So we'll just write that in. So we have 1 over s. Then we'll have, because the minus and the minus will give us a plus. So they have minus e to the minus st, and t is now 2. So we have minus 2s over s. So we can combine all of these terms, and it's a very straightforward thing to do. And once we do that, we bring out this common factor 1 over s, and then we write everything, and then we can combine these terms and so on. But that's a simple math that you can do. We can just leave the answer like this. So this is the illustration of how to find the Laplace transform of a periodic function. We have seen that it's simply equal to f1s multiplied by 1 over 1 minus e to the minus st. And then f1s is just the integral from 0 to t, f of t times e to the minus st dt. So thank you very much for watching.